Hello, and thank you for attending DVCon. My name is Aimee Sutton, and I work for Imperas Software. My co-presenter today is Mike Thompson from the Open Hardware Group. We're going to take you on a journey that our organizations have been pursuing since 2019. This journey follows the evolution of a methodology for RISC-V processor verification, which started with an ad hoc approach and ends with a robust standards-based approach that is in use today. Today's talk is going to cover the following. We'll start with an introduction to the Open Hardware Group and their mandate, and then we'll talk about 3 different incarnations of the Open Hardware Group's RISC-V processor verification environment called Core5 For each incarnation, we will describe the operation of the environment and any challenges, deficiencies, and incremental improvements over the previous. Between the 2nd and 3rd generation, we'll discuss the RISC-V verification interface. We'll talk about asynchronous event verification, which is a constant challenge throughout this journey, and we'll end with a slide describing future work. And now I'll turn the presentation over to Mike, who will speak about the first 3 bullet points.
Thanks, Aimee. As Aimee said, my name is Mike Thompson. I am the Verification Director of Engineering for the Open Hardware Group. Not a lot of you have heard of the Open Hardware Group, I'm sure. We are a not-for-profit global organization registered in Canada and Europe. We've got 100 members and partners from all over the world, United States, Canada, all over Europe, all over Asia. And our members, both corporate and academic, collaborate in the development of open source tools or open source cores, related IP, tools, and software. Our primary focus is the Core5 family of open source RISC-V cores. And if you are familiar with RISC-V and are operating in RISC-V circles, anytime you see something with a Core5 in front of it, that's how you know it's an open hardware artifact. What we'll be talking about today is probably the largest project within the Open Hardware Group. It's called Core5 This is a system Verilog UVM environment specifically targeting RISC-V processor verification. So this is a verification environment that's specifically targeted at verifying a RISC-V core. This is an open source artifact. It's available on GitHub right now. Go to that URL, or just use Dr. Google to search for Open Hardware Group Core5 Core5 was developed by the Open Hardware Group's Verification Task Group. Verification Task Group is made up of the same members that are members of the Open Hardware Group. We get big contributions from organizations like Silicon Labs, Imperas, EM Microelectronic, and there's ongoing work by Silicon Labs again, Imperas again, TELUS, Dolphin, NXP, Intrinsic, and many, many others. As Aimee said, Core5 was created in 2019 and has been in constant evolution ever since. We've condensed the evolution story down into a 1, 2, 3 story. It wasn't quite as smooth as that, but it really does, the story does work that way. This environment is in use today to verify 6, soon to be 7 different cores within the Open Hardware Group. It's also being used in many academic and commercial organizations today that are outside the Open Hardware Group. It's an open source artifact. It's available for you to use. I want to talk about the first generation of Core5 and if you've ever done any verification, and if you're a DVCon, I know you have, this picture will look very familiar to you. We've got the UVM environment, which is composed of a number of components, agents, the device under test, and a reference model, and maybe a scoreboard. So that's basically what we're looking at here. What's different about this is the input stimulus is a set of test programs. These test programs are generated by humans, a C program or an assembler program, or they can be machine generated. Either way, the machine code is fed into the instruction memory for the RTL, the device under test. The same program is fed to the instruction memory of the reference model, and both the reference model and the device under test run the same program at the same time. And as the execution of the program progresses, the state of both are compared as each instruction is retired. We call this step and compare. So 3 key points here about this verification environment. The DUT and the reference model execute the same program at the same time. As every instruction retires, state variables are compared. Mismatches are reported as errors, of course. And once again, we call this the step and compare method. External interrupts and debug requests, we call these asynchronous events. These things are fed both to the design under test and to the reference model. So both of these models see the same asynchronous events, and that affects their behavior accordingly. The Imperas OVPSIM instruction set simulator was used as a reference model in our first generation. Using an off-the-shelf commercial ISS as a reference model saved us an enormous amount of time in development effort of the verification environment, allowed us to get up and running very quickly. An interesting artifact is that an ISS, if you've ever used one, you know that it works at a different level of abstraction than an RTL model of the DUT would be. Time for an ISS goes on instructions. So there's instruction 0, there's instruction 1, there's instruction 2, whereas time progresses in an RTL model on clock cycles. And a clock, you may take 1 clock cycle to execute an instruction, or you may take, in our case, up to 30 cycles to execute an instruction. So there's a different view of time, and this creates some interesting artifacts. Another interesting tidbit about the first generation is the tracer that was used to expose the internal state of the RTL was a very ad hoc design. It was essentially whatever was there when we started verification of the RTL, and this led to some interesting challenges. I've hinted on a couple of these challenges. The first is that the ISS is always receiving async events, debugs, interrupts, bus errors at the start of every instruction. And this is not the view that the RTL has. So the RTL and the reference model are seeing things at different times. This resulted in a large number of false negative comparisons, and each one of these had to be debugged and resolved on an individual basis. Here's the problem. When you get an asynchronous event, like a debug request, like an interrupt, like a bus error, the processor core will produce side effects. So for example, when you enter debug mode, the device under test will automatically update the DPC CSR. When that is done depends on when the core recognizes that the debug event happens. When that happens depends on the type of instruction we're executing and how long it took, maybe on some latencies on the instruction or the load store bus interfaces. The reference model never sees that. The reference model always sees a debug request at the start of an instruction. So this made the environment very prone to a lot of cycle accurate bugs. So this motivated us to make a few changes. And these are manifested in this diagram here, what we're calling the second generation of Core 5 Verif. It looks very similar to the first generation because it is. There are several interesting things that are different about it, though. The first is the debug requests and the interrupts, which come from UVM agents, they are fed only to the device under test. They are not connected to the reference model as they were in the first generation. You may also notice that the tracer now has a name, RVFI. That stands for RISC-V Formal Interface. I'll be talking more about that in a minute. But the crucial aspect here is that we have a much more rigorously defined tracer interface. And, excuse me, the debug requests and the interrupts are being fed to the RTL, not the reference model. The biggest improvement we made was to get rid of that ad hoc tracer from the first generation of Core 5 Verif and replace it with a well-specified, rigorously defined, cleanly implemented tracer. We started off with something called the RISC-V Formal Interface. This was first developed by Claire Wolf. If you've been involved with RISC-V circles for any amount of time, you will know her name. She's very big in formal verification, and she developed the RISC-V formal interface to simplify the job of formal verification of RISC-V cores. We use it for that, but we most often adopt the RVFI for use as a tracer interface because it's got almost everything that you would need for a tracer interface for simulation. Using this has allowed us to greatly simplify the step and compare logic. I want to talk about the Core 5 tracer. The Core, once again, remember I said, if you see Core 5 in front of anything, it means it's an open hardware artifact. The Core 5 tracer is a straight line derivative of the RISC-V formal interface, the RVFI. It's been enhanced for the needs of simulation verification, most specifically the needs of the step and compare methodology that we've been discussing. The big thing that it does here is it unambiguously defines when an instruction is retired. The RTL does not have to, or the test bench does not need to guess about this. The tracer interface is explicit about when this happens. And it also unambiguously reports synchronous traps and asynchronous exceptions, such as those debug and interrupts I've been talking so much about. And it exposes all of the state of the core, the program counter, all of the CSRs, and all of the GPRs to the outside world so that the test bench can see what's going on inside the core. I want to talk a bit about asynchronous events with the Core 5 tracer. Remember, the reference model is not connected directly to these asynchronous events anymore in the second generation of Core 5 Verif. So it relies on the tracer to signal when these things happen. The Core 5 tracer monitors and reports these events and informs the reference model to interrupt its normal program flow. I'll give you an example. One of the ones that's very challenging to deal with is debug request. For the Core 5 tracer, we've added a couple of signals. One's called RVFI debug. This is a vector that indicates the debug cause, and the other one is called debug mode. Debug mode is asserted whenever the core retires an instruction while it's in debug mode, and RVFI debug signals the cause, and it does so on the first instruction that was executed in debug mode. So now the test bench is observing these signals. It has unambiguous knowledge about when the core decided to enter debug, and it can make decisions based on that information. So the second generation really improves things quite a lot, but there were a lot of challenges. Asynchronous event handling still was an ongoing challenge. It was very difficult to provide independent verification of async events that happen within an instruction cycle. So for example, you might get multiple interrupts within an instruction cycle, and the reference model cannot determine the timing information of those because they all show up at the same time as far as the reference model is concerned. They show up at different times as far as the RTL is concerned, but the reference model cannot know that. Another thing about this is, even though the Core 5 tracer is a significant improvement over the ad hoc tracer we used in generation 1, it still is a bespoke tracer, which means that it's custom to the core that we're developing. So there's an awful lot of work that is basically tied to a specific core, and this makes reuse very challenging. So I'm now going to hand the baton off to my colleague Aimee, and she's going to go through some of the improvements that we've made in the third generation of Core 5 Verif.
Thank you, Mike. And now we're going to talk a little bit about the RISC-V verification interface. So the experience with the first and second generation Core 5 Verif environments led to the realization that some components are common to all RISC-V processor DV efforts, and common components should have standard interfaces. This realization led to the development of RVVI, the RISC-V verification interface. RVVI is an open standard, and it's the result of collaboration between Imperas and other members of the Open Hardware group. The source code for RVVI is publicly available on GitHub at the link at the top of this slide. And the purpose of RVVI is to standardize the communication between a test bench and a RISC-V design under test, and also the test bench and a piece of RISC-V verification IP. There are three parts to the RISC-V verification interface. There is the RVVI trace, RVVI API, and RVVI virtual verification peripherals, or VVP. In the next slides, we're going to take a look at the first two, where the third one is outside the scope of this presentation. RVVI trace defines the information that a piece of RISC-V verification IP needs in order to check the proper behavior of the processor under test. The information needs to be extracted by a tracer, which we've talked about in the previous slides. And a tracer itself is not part of RVVI. Its implementation is dependent on the RISC-V core. However, RVVI defines the requirements for the tracer so that when you use RVVI, designers and design verification engineers will know what the requirements are at the beginning of their project. RVVI trace is specified as a system Verilog interface, and it includes functions to enable the handling of asynchronous events. So those are the events that we've talked about, like interrupts and debug requests that occur outside the normal flow of a program. And those are the events that have been historically difficult to manage in previous iterations of Core5 The second part of RVVI we're going to talk about is the API. So this is the function level interface between the test bench and a piece of RISC-V verification IP. It defines a standard set of functions that verification IPs need to implement in order to comprehensively verify a RISC-V core. For example, there are functions to get and set the current value of registers in the verification IP, and functions to invoke comparisons between the device under test and the verification IP's processor reference model. It supports a co-simulation continuous comparison methodology, which is an improvement over the previous step and compare methodology. And there are both C and System Verilog versions available. And now we're going to look at the third generation of Core5 So the major differences over the previous generations are that the Core5 tracer has now been replaced by an RVVI compliant tracer. The Imperas reference model has been replaced by Imperas DV, which is a verification IP for RISC-V processors that incorporates a reference model. The step and compare logic has been eliminated. As we saw in the previous slide, verification IP now uses continuous comparison. And this block diagram represents an example of RVVI compliant verification IP. This is the Imperas DV VIP that's used in the third generation Core5 environment. Imperas DV connects to the processor under test using RVVI trace. It contains Verilog modules that are used to sample functional coverage, produce a detailed trace log file, and drive the RVVI API. The trace to API module implements the RVVI API, and these methods are used to communicate with the Imperas RISC-V processor reference model. And to use Imperas DV, OpenHW only needs to develop and connect the tracer. The comparison and checking is done by the verification IP, which has simplified the verification task. Let's talk a little bit more about asynchronous events, a challenge that has been present throughout the RISC-V DV journey, and it's now also addressed using Imperas DV. This picture is called a staircase waveform, It's a bit of an extreme scenario where many interrupts are triggered one after another. An architectural model of a processor can't predict exactly which interrupt will be taken by the processor under test because it doesn't model the processor's microarchitecture. So to solve this dilemma, Imperas DV has something called a predictive engine. It will receive all these net changes as a set over the RVVI trace interface. And then it will analyze all the potential legal responses to these nets that the processor could take. And it will verify that the processor follows one of these legal paths. If it does not, then it issues an error. And so what this has done is eliminate the need for custom code to try to model handling of each interrupt or each similar asynchronous event scenario. So future work. The members of the Open Hardware Group's verification task group are continuing to work to improve RISC-V processor verification. One of the upcoming improvements planned to Core 5 Verif is to use machine-generated functional coverage code for the RISC-V ISA. This is a very reasonable thing to do because functional coverage code derived from the ISA is standard and doesn't change between different processors that use the same extensions. And it will be done using data sampled from the RVVI trace interface. There is a task group in Open Hardware dedicated to advanced verification techniques. This is the ARVM group, Advanced RISC-V Verification Methodologies. And you can find out more about their ongoing projects by visiting the link in this slide. And I'll leave you with some references so you can learn more about active Open Hardware Group projects, where you can find the Core 5 verification environment on GitHub. There's a quick start guide to help you get going with Core 5 Verif. And there's a link to RISC-V processor design verification solutions from Imperas. Thank you for attending our talk today. I hope you had an enjoyable time at DVCon.